I used to think the database was the single source of truth. Then I got into distributed systems and realized there are many truths. It's like discovering the world isn't flat. It's a mind-bending shift. So what does it mean when we talk about consistency in this world of multiple truths? Stick around, because by the end of this video, you'll understand one of the biggest challenges in modern software engineering. Let's start with a simple question. When you update a piece of data, say your profile picture on a social media app, do all your friends see the new picture at the exact same time? The answer is almost always no. This is the essence of consistency. Do different locations see the same version of data at the same time? In a simple, old-school system with one computer and one database, this is easy. Everyone reads from the same single source. But modern systems are rarely that simple. They're distributed, spread across the globe for speed and reliability. And that's where our problems and our story begin. To make this crystal clear, let's think about it like a massive e-commerce logistics network. Imagine we have a central, main warehouse. This is our primary database. It's the ultimate authority, the original source of all our inventory data. Every single item we sell is first registered here. When a new shipment of 10,000 new super widgets arrives from the factory, their details are entered into the ledger of this main warehouse first. It is the single definitive record. Running a global business from a single warehouse is a terrible idea. If a customer in another country places an order, shipping from the main warehouse would be slow and expensive. And what if that main warehouse has a fire or a flood? Your entire business goes down. So what do? You build branch warehouses in different regions. In the world of databases, we call these replica databases. These are copies of the main warehouse's inventory. They exist to serve local customers faster and to act as a backup if the main warehouse goes offline. When a customer in Europe wants to know if those super widgets are in stock, they don't have to check with the main warehouse in North America. They can check their local branch warehouse in Germany, which is much faster. Now let's add another layer. Even within a city, getting a package from the local branch warehouse can take a few hours. What if you need something like right now? This is where smaller, forward warehouses or local pickup points come in. These are our caches. A cache is a super-fast, temporary storage that holds the most frequently requested items. For our super widgets, maybe the top 10 most popular models are kept in these small, hyper-local spots. When a user asks for product information, the system first checks this lightning-fast forward warehouse. This avoids a trip to the bigger, slower branch warehouse, making the user's experience feel instantaneous. So now we have a main warehouse, several regional branch warehouses, and countless tiny forward warehouses. The big question is, do all of these warehouses have the same perfectly synchronized inventory ledger at every single moment? This is the core problem of consistency. If the main warehouse receives a new shipment of 500 widgets, how quickly do the branch warehouses update their own ledgers to reflect this? And how quickly do the forward warehouses get the memo? This delay is what we call replication lag. It's the time it takes for an update made in the main warehouse, our primary database, to be copied or replicated to the branch warehouses, our replica databases. During this lag, the truth is different depending on where you look. The main warehouse's ledger might say there are 10,500 widgets. But for a few seconds, or even minutes, the German branch warehouse's ledger might still say 10,000. And the local cache in Berlin? It might still be showing the old stock information from yesterday morning. So who is right? The main warehouse says 10,500. The branch says 10,000. The cache might have an even older number. The shocking but crucial insight here is that they are all right from their own perspective, at that specific moment in time. In distributed systems, having multiple slightly different versions of the truth coexisting is not an error. It's the normal state of affairs. This happens because we've chosen to prioritize other things, like performance. Reading from a local replica or a nearby cache is way faster than going all the way to the primary database for every single request. We accept a small delay in consistency in exchange for a huge gain in speed and user experience. Imagine the alternative. To ensure perfect consistency, every time someone wanted to view a product, the system would have to lock everything down. It would have to go to the main warehouse, get the absolute latest number, and only then show it to the user. And if someone made a purchase, the system would have to halt all operations worldwide until every single warehouse and cache confirmed they had updated their ledger. The entire global system would grind to a halt. It would be perfectly consistent, but also unusably slow. So we trade a little bit of consistency for availability and speed. We accept that for a brief period, the data might be slightly stale in some locations. This leads us to a fundamental dilemma in distributed systems. Let's make our logistics metaphor a bit more dramatic. What happens if the communication lines between the main warehouse and a branch warehouse are cut? Say, an undersea internet cable gets damaged. The German branch warehouse is now completely isolated. It can't receive updates from the main warehouse, and it can't send its own sales data back. It is now operating on its own, with potentially outdated information. At this point, the system has to make a critical choice. Does the German branch shut down completely? It could refuse to serve any customers, saying, "Sorry, I can't guarantee my inventory data is 100% accurate, so I'm closing until I can talk to the main warehouse again." This choice prioritizes consistency. It ensures no one in Germany buys an item based on wrong information. The downside is that the entire European operation is offline. The system is not available. Or does the German branch stay open? It could continue to operate, selling items based on the last known inventory data it has. It would serve its customers, and the business would keep running. This choice prioritizes availability. The system is up and running, which is great for business and user experience. But the risk is that it might sell the last super widget, not knowing that the main warehouse's ledger already shows it as out of stock. When the connection is restored, there will be conflicts to resolve. This is the classic trade-off known as the CAP theorem, which states that in the event of a network partition, a system must choose between consistency and availability. You can't have both. So as we've seen, that single source of truth I talked about at the beginning is more of an ideal than a reality in large-scale systems. The truth gets replicated, cached, and spread across the globe, creating temporary parallel realities. Managing this is the art and science of distributed systems engineering. There are many strategies to handle this, like eventual consistency, where systems are designed to accept that data will be out of sync for a while but will eventually converge to the same state. Or techniques like read your writes, which ensure that at least you personally will see your own updates immediately, even if others don't. Understanding this trade-off between consistency and availability is key to understanding how the modern internet works. From social media feeds to online shopping carts, engineers are constantly making decisions about which to prioritize for any given feature. The next time your social feed seems a bit out of order, or a product stock level changes when you refresh the page, you'll know why. It's not a bug. It's a feature of living in a distributed world with many truths. Thanks for watching. If this journey into the world of distributed systems sparked your curiosity, make sure to like, subscribe, and hit that bell icon so you don't miss our next video where we'll dive deeper into the CAP theorem. See you in the next one.